So welcome back. Bafundi, we are starting our very last topic for the year. It's probability and counting techniques, and we're going to start off by just revising what we should know about probability. There's nothing new that we need to teach you in the probability space, so we need to go over what you should know, but we are then going to do some probability with the new stuff, which is the counting techniques. So let's dive straight in. We're on page 73. And we're going to go over this quite quickly, but it's really a summary of everything that you should know. There's only two formulas that get given, and those are shown in blue. Other things that we think you should know are shown in red, and we know that your workbook's not got color in it, but maybe you just want to sort of highlight important things as we go. So when things are shown in red, really important. So what probability is, it's a measure of likelihood of something happening. And a really important idea is that all probabilities range from 0 to 1, including 0 and 1. And a probability of 0 means impossible. It will not happen. Right? An example would be throwing a 7 when you throw a regular die. Okay, we call it a die. It's actually, most people say dice, but it is actually a die, but a dice or die. Okay, a probability of 1 means guaranteed. It's certain to happen. Okay, sample space is all the possible things that can happen. So for example, if I toss a die and a coin, there are actually 12 things that can happen. And I'm going to write them down. We normally write our sample space in a set with this squiggly bracket. Okay, we could get heads on the coin and 1 on the dice. We could get heads on the coin and 2 on the die. Heads and 3. Heads with a 4, heads with a 5, heads with a 6, tails with a 1, tails with a 2, tails with a 3, tails with a 4, tails with a 5. I'm trying to fit them all in on one line, I don't know why. Tails with a 6, and that's that. All right. There are actually 12 things that can happen. The probability of an event happening, now this formula gets provided to you. It gets given to you in tests and exams. And what it says is it's the number of ways that can happen divided by the total number of things that can happen. So if we go back to this previous example, what's the probability they get an even number on the die and tails on the coin? So out of our 12 things that can happen, how many of them satisfy even on the die and a tails on the coin? All right, well, let's just have a look. It's obviously this one over here, T2. It's also T4 and it's T6. So our final answer is going to be 3 out of 12, or we could write it as 1/4, or we could even write it as 25%. Okay, very often probabilities are written as percentages just because they're easy to sort of interpret and to understand. All right, now probability on the 3 or on the 3 on the die or tails on the coin. So now let's see which ones we need to count. Okay, we must count this one because we got a 3 on the die. We must count this one because we got tails, this one because we got tails, this one because we got tails. So in fact there are 7. 1, 2, 3, 4, 5, 6, 7. 7 out of 12. All right. Now, what you'll notice is that included in the word or, for or we always include both. Okay, and I'm going to give you an example. If your mother said to you, you can go out with your friends when you've tidied the kitchen or when you've done your homework. So if you've tidied the kitchen, can you go? Yes, you can go. If you've done your homework, can you go? Yes, you can go. If you've done both things, yes, you can go. Right. So notice that here we were talking about 3 on the die or tails on the coin. We don't count this one twice, but we definitely count it. Okay. All right. We'll come back to that. Right, we use these symbols for and for or. So and is almost like an N without a little stalk on it, and U for an or. Okay, the probability of all the things that can happen must add to 1. we say that they are exhaustive. Okay, so I draw out a bead from a bag. This bag's got green, red, and purple beads. The probability that it's a red bead is 23%. The probability that it's a green bead is 15%. What's the probability that it's purple? So there's only three things that can happen here. We've got the probability of green. Sorry, let me just try and write a bit more neatly. We've got the probability of green is 15%, 0.15. We've got the probability of red is 0.23. And then we've got the probability of purple. And we don't know that. Okay, let's let it be X. All right. What do we know about these three probabilities added together? They must add to 1. All right, because there's nothing else that can happen. So we're going to read this again. The probabilities of all the things that can happen must add to 1. We can't get a yellow bead. There's no yellow beads. Okay, the bead either has to be green or red or purple. So we now know that if we add all these things up, 0.15 plus 0.23 plus X, that must come to 1. Right, so now we're solving a really simple equation. If we add these two things, we get 0.38 plus X equals 1, or equals, plus X equals 1. So X will be 1 minus 0.38. X will be 0.62. So the probability of a purple bead is 0.62. Right. We also have the idea of something not happening. So the probability that an event does not happen can be shown, and we've shown it in two different ways here. We can show it with a line on top, but we can also show it with a little apostrophe, and you need to be familiar with both of those. And the probability of an event and its complement, that's that it doesn't happen. All right, that's complement with an E, okay, not complement with an I. When you compliment someone with an I, you say something nice. Oh, you're very beautiful, or you're very good at maths, or whatever it might be. That's a compliment. With an E, it's the balance, okay? All right. And so the probability of an event happening plus the probability of it not happening is always 1. So for example, if you hear on the weather forecast, there's a 72% chance of rain tomorrow, then 1, which is 100%, minus 72, 28%. Right. 28% plus 72% is 100%. And remember, and hopefully you're comfortable with this, 100% is 1. Okay. All right. Now this is a big idea. The complement of at least 1 is none. This is really really important and worth kind of learning. Whenever you see at least 1, the easiest way of working that out is going to be working out the complement. Right, and I'm going to show you. I toss a coin 3 times. What's the probability that I get at least 1 head? All right, so there are actually 8 things that can happen, and soon we're going to understand why there are 8 things that can happen. I'm going to suppose that I toss a head on the first throw. Then on the second throw, I could toss heads or I could toss tails. Okay. Now, if I toss a head on the first throw, there's now again 2 choices. I could toss heads on the third throw as well, or I could toss tails on the third throw. So we've got heads, tails. Here, if we toss tails on the second throw, we could get tails on the third throw, or we could get heads on the third throw. Those are the only 4 things that can happen if I toss a head first. But I can also toss a tail first. So, or each of these can be repeated, but with tails first. Tails, heads, tails. Tails, tails, tails. Tails, heads, heads. And tails, tails, heads. there are actually 8 things that can happen, and we're going to teach you how to count that, how to calculate that soon. All right, but those are the only 8 possibilities. If you look through them, you'll see those are all of them. Now, which ones must I count if I want at least one head? Here, do I get at least one head? Yes. Here, yes. Here, yes. Here, yes. Here, yes. Here, yes. Here, no, and here, yes. All right, so in fact, in all but one of them, I get at least one head. So the probability of at least one head is 1 minus the probability of no heads. So it's actually going to be 1 minus 1/8, because it's only one where we don't get one of the 8. So there's actually a 7 out of 8 chance that if you throw a coin 3 times, you will get at least one head. That includes getting 2 heads or 3 heads. Okay, all right. Suppose there's a 30% chance of rain on each of the following 4 days. What's the probability of rain what's the probability of rain on at least one day? That we have at least one day of rain. All right. Okay. So yeah, this question is actually a little bit problematic for us right now, but we can do it. It's going to be 1 minus the probability of no rain on each day. Okay, now what we're going to get into, and we'll get into it right now, in fact, on the next page, is the whole idea of independence. All right, if we're assuming that these days are independent, then we've got a 30% chance of not having rain on the first day, and then we want that to happen again, so we multiply, and we will talk more about this shortly. This might be slightly out of order, but you should remember it from previously. When events are independent, we multiply their probabilities. So let's just check what this final answer is going to come to here. All right, it's going to come to 1 minus 0,3 to the power of 4. 1 minus 0.3 close bracket power 4, and we get 99%. Okay, 99% chance of rain on at least one day. Sorry, my mistake. We want no rain, probability of no rain. These are not 0.3, these are 0.7. No rain on the first day is 70%. No rain on the second day is 70%. Right, my apologies. Okay, let's work that out again. We can just go and rewind that calculation and change that 3 to a 7. And yeah, that's looking a bit better. About 76%. All right, approximately 76% chance of at least one day of rain. Okay, right, now we're getting on to a really big idea, which we've just spoken a little bit about. This is not given, it's not provided, but it's ebalulekile. Okay, very, very important. If events are independent, then we can multiply the probabilities to find the probability that they both happen. All right, but I want to show you something that's really important here. This arrow has got a double head on, which means that we can read this from the left to the right, but we can also read it from the right to the left. So in other words, if this is true, then the events are independent. If the events are independent, then this is true. Okay, and going back to the rainfall, we said let's assume that each day is independent. The weather is independent on each day. Right, so we could multiply the probabilities. Okay, now this question asks us to test, are A and B independent if these things are true? Now, if they're independent, okay, then this must be the case. So let's work out the probability of A times the probability of B. It's just going to be 0,3 times 0,7. 3 times 7 is 21, so this must be 0,21. Okay, now That is not equal to, probability of A and B, we were told, is a half, 0.5. These things are not equal. So we've got that the probability of A and B is not equal to the probability of A times by the probability of B. Because of that, they are not independent. If those were equal, then we could read this from the right to the left, the events would be independent. So they are not independent. Okay, now we can use this exact same idea to test for independence in what we call a two-way contingency table. And you may remember this, so let's see if you can just test on this data, left-handed people and right-handed people, and whether or not they drink tea. Test whether liking tea is dependent or independent of which hand one uses. Pause and have a go, and then we'll have a look at it shortly. Okay, so we're going to take any combination. We're going to talk about someone who likes tea and is left-handed. Okay, and we're going to work out that probability. Let's have a look at what that is. How many left-handed people are there who like tea? And it's just these 12 people here. So the probability of choosing one of those people is 12 out of 336. Okay, we can get that on our calculator. Let's just get it in decimal form. 12 out of 336. And it actually works out to 1 out of 28. Let's just write it as 1 out of 28. Now what we're going to do is we're going to take the product of the separate probabilities. So we're going to work out the probability of liking tea, and we're going to multiply by the probability of being left-handed. Let's look at how many people like tea. Well, there are 48 people that like tea. So the probability that we find someone who likes tea is going to be 48 out of 336. What's the probability that someone's left-handed? Well, there are 84 left-handers. So 84 out of 336. Okay, we're going to calculate that product. Let's bring up our calculator. So we're going to go 48 out of 336 times 84 out of fraction button 336. And we get 1 over 28. We get exactly the same answer. Now, since probability of T and left-handed is equal to the product of T and the product of the probability of T and the probability of left-handed, that product, they are independent. Okay, and what that means when we say they're independent, the one thing doesn't influence the other thing at all. So in other words, if you find a person, whether they're left-handed or right-handed, their chances of being a tea drinker will be the same. There's no connection. Okay, so this here is a really big idea. I'm going to put a big red star next to it. Okay, because we're going to come back to that. All right, the next idea is something called events being mutually exclusive. Now, when events are mutually exclusive, they cannot both happen. And I'm going to give you an example, all right? For example, being a learner at Shea O'Connor School and being a learner at Imnyezaneni are equal. There's no one. There's no one who's a learner at both of those schools. Okay, that's mutually exclusive. When things are mutually exclusive, the probability that they both happen is 0. All right. And this arrow, just like the last time, this arrow's got a double head on it. All right. When the probability of A and B is 0, the things are mutually exclusive. So, example of mutually exclusive, being a learner at whatever school you like, let's call it Shea O'Connor, and being a learner Okay, I'm going to say at Tendela. It's nice and short to write Tendela. Okay, those things can't both happen. Let's look at an example of non-mutually exclusive where they can both happen. Being in grade 12 and being at Jabula. Okay, those things can both happen. There are grade 12s at Jabula. The probability of finding a grade 12 at Jabula is not zero. And because it's not zero, they're not mutually exclusive. This here is a really big idea. And what we're going to do, we're going to put a big red star next to it. All right. So I'm going to, in order that we can come back to it and talk about it again. All right. We're going to look in the next lesson. We're going to remind ourselves of this rule. This rule gets provided. It's the addition rule for probability. And before next lesson, in preparation for next lesson, perhaps you want to try these three examples. Okay. We'll see you next time.